Good morning, everyone. I'm Chen Junwei. Here is my presentation. And as we know, the time-resolved velocity and the pressure fields are very important in research and engineering, such as locate the source of noise and in boundary layer research and compute the aerodynamic loading of vehicles. Usually, the velocity is measured by the probe in pointwise or measuring by the pressure-sensitive paint on the surface of objects. And for this, we cannot have the pressure distribution in the field. And indirectly, we can compute the pressure distribution via Navier-Stokes equation here, which contains the spatial derivative of velocity field, which is naturally produced by PIV, and the temporal derivative of velocity, for which we required the PIV measurement in high frequency, so that we called it the time-resolved PIV. And here I should introduce two kinds of measurement method. One is PIV by spreading the particles inside the fluid and take photo particles in short time interval. We are able to compute the velocity field. And the second is probe measurement. We install the probe inside the field and measure the velocity or pressure pointwise. And here is a problem of sample rate. The PIV is restricted by the sample rate on the frequency of laser and cameras, but probes can offer the sample rate even 1,000 times higher than the PIV. So our objective is to obtain the time-resolved velocity and the pressure field from low-speed PIV and fast probes. Here is a sketch of the data-driven measurement. We are used to combine the snapshot of flow field and probe data. As we can see, we are using the neural networks or EPOD to fit the relationship between the snapshot of flow field and the probe data. After that, once introduced the time-resolved or real-time probe data, we can reconstruct time-resolved velocity field. After that, we are able to calculate the time-resolved pressure field using Navier-Stokes equation. And here is my lot map. There are several items proceeding. Last year, I have presented the part of EPOD and the pressure, and they are work really well in the convective dominated flows. And this year, I'm more focused on sensor positioning and machine learning. One important problem in the combination of probe data and PIV snapshots is about where to place the probes. There are several methods already published by other groups, such as QR pivoting and digital entropy, and they work really well in sensing the temperature of ocean or compressed sensing of human face. And in our fluid experiments, the intrusion is quite issue to be concentrated on, because we are placing the probes in the fluid, and not to influence the flow field so much. For this reason, we are placing the probes by the downstream edge of the field and using the time series such that they are look as if the signal across the whole field. And if the turbulent is fully frozen, it can be considered as a signal across the whole domain. For this, we can see in the second row. For this reason, we can consider that using the long sensors as a replacement of the probe with time theories. But one thing is to be concerned that the PIV snapshot is not time resolved, so we cannot use the long sensors in the second row to reconstruct the time resolved flow field. And if the turbulence is not quite frozen, the data of the flow is losing the fidelity before coming to the place of probes. So we are considering masking some part of the raw sensor data, such as to simulate the probe with time series. And this picture shows the heat map, which corresponding to several optimal sensor placement by traversing all the possibility of by traversing all the combination of possible place. And we can see there are two peaks out of the wake, which tells us not only to put the probes inside the wake, but also out of the wake. And by introducing the third type of probe, we can see the peak of raw sensor mask is more close to the probes with time series, which we are using in the measurement, so that we can consider that the raw sensor mask is a better surrogation of probe with time series comparing to the one without masking. Also, the test on the channel flow from the database of Johns Hopkins also confine this regular, and we should notice that the probes are more preferred to the wall position, but not very close to there, because the data is losing fidelity so fast if we put it too close to the wall. And the result will be presented in the future article to be submitted. Another thing is machine learning. And in typical machine learning, we are using one snapshot of probe data and one snapshot of PIV snapshot and fit their relation. And this is called supervised machine learning. And as we know, the cost of storage and computation, the cost of storage and computation for PIV snapshot is much higher than the probe signal. So here comes the problem. If we can use more probe data that not labeled with the PIV snapshot, and the answer is yes. By introducing another neural network fitting the time derivative of the PIV of the coefficients from the probe data, we can we can train the model using the reconstruction of the coefficient and its time derivative. And this part can be even trained more without PID snapshot. And this is called unsupervised machine learning. So the semi-supervised machine learning is the combination of supervised and unsupervised one. And we found the improvement of supervised machine learning has 73% improved comparing to EPOD, and semi-supervised machine learning has 36 percentage improvement to the supervised one. Also, I'm preparing for the experiment, and after that, I will submit 2 articles, and here are my achievements and future plans. Thank you.